Hi, all. Welcome. I'm delighted to have Professor Arindam Chowdhury, who is at Florida International University Civil and Environmental Engineering. He is going to talk at the CAE CET seminar on advancement in community resilience using innovative experimentation and convergence framework. Professor Chowdhury is conducting groundbreaking research at the Wall of Wind WOW facility. Under his direction, the team has had significant impact in mitigating hurricane damage by enhancing building codes, validating, patenting innovative mitigation technologies, and developing many new products. He is currently leading a massive multi-institutional project funded by NSF to support the design of a national full-scale testing facility capable of generating wind speeds up to 200 miles per hour. I think many of you can appreciate how much of an advancement that would be. And this would be combined with a water basin to simulate storm surge and wave action. He has won too many awards for me to list, but these include the NSF Career, the President's Council World's Ahead Award from FIU, among others. He has a PhD from Iowa State, MTech from IIT Mumbai, and a BCE from Jadavpur University. Thank you very much, Professor Chowdhury, for doing this, and the floor is all yours.
Thank you, Pranoy. Glad to have the opportunity of this seminar at the Department of Civil and Architectural Engineering. So thanks for the opportunity. So I'm going to talk about advancement in community resilience using innovative experimentation and convergence framework. We'll talk about some of my career background, what I did with my earlier research, and then talk a little bit about the NHERI Wall of Wind facility, some of the case studies, education and outreach, and finally go to the bigger project that we are involved. So I think I can skip this slide because Pranoy already introduced me on all of that. My research started with bridge elasticity, so it's relevant to long span bridges, as you can see, and then the main impact was from the Tacoma Rose Bridge that actually failed on the video that you can see here. So this failure of the Tacoma Rose led to a lot of researchers working on bridge elasticity, how the bridge vibrates in wind, and we can model in the wind tunnel test section various degrees of freedom of the bridge under wind loads, and these are some equations that apply to those motions. From there, in the laboratory, my research was to simulate the actual flutter. As you can see, this is a couple flutter of a section model of the bridge in the wind tunnel. And we came up with theories that long span bridges can be designed using those theories. So that was my background. Then when I joined the Florida International University, I started looking at full-scale and large-scale testing of even other type of structures, buildings, bridges, traffic signals, transmission towers. So we got funded by NSF's NHERI program, which is the National Hazards for Engineering Research Infrastructure. They have all these facilities that you can see on this particular picture. And this is called actually the NHERI wheel, we call it. And we are one of the two facilities that can do the wind simulation. So this is our facility, Florida International, and then we have the University of Miami in Gainesville. We have an open jet wind tunnel, some of you already have seen. And our unique capability is to produce like a category 5 hurricane wind speeds and test large scale models or even full scale models. So these are various parts of the wind tunnel. We have the control room. We have an atmospheric boundary layer simulation technique using automated roughness on the floor. We have a huge turntable, and we also have a staging area where we can build models. The uniqueness of our facility is that we can do large scale and full scale testing. Let me see if I can move away from that particular view. I probably have to kind of Bruno, can you still see my screen?
Yes, I can see your screen.
Okay, sorry about the. Okay, so yeah, so you can see like this is the testing of a large scale roof, a standing seam metal roof in the wind tunnel. And you can capture the vibrations. You can also capture the failure modes like clip rupture or seam line disengagement on some of the right hand side pictures. And what you get here, you don't get in the standard ASTM or other kind of static or even dynamic lab tests. And you can capture this vibration and the failure mode. So that's the advantage of the wall of wind, that we can look at failure modes. We can improve the design. We can also inform the current standards that can be improved using some of these findings. We also know that hurricanes bring a lot of wind-driven rain. And the wind-driven rain has two ways of getting into the building: the direct rain coming, as you can see on the left-hand picture, and then surface runoff, which percolates from roof or the wall and just goes inside a crack or an opening. So we can simulate all of that at the wall of wind. So this is a simulation of rain on a large-scale model. One of my PhD students graduated with this particular topic, looking at how to scale down rain based on realistic rain measurements in the hurricanes and look at water intrusion. When we get such data, we can come up with various rain intrusion coefficients on the building. So you can see some of the contour plots on the left-hand side. And how this is used to inform risk modeling. So insurance companies can take this model and they can enhance their capability of producing like risk estimates under wind and rain. And they can compare that with the actual losses from claims after hurricanes. And on the right-hand side graph, it shows how using the wall of wind data, there was a significant improvement in matching the simulated risks with the actual losses that they see from the claim. So this was a significant improvement that we did based on testing. There are other things that can be done as well. Like, for example, this picture shows like impacts of rain on windows. You know, we have seen that in past hurricanes, even under low category hurricanes, the rain can come inside the sill, from the sill of the windows. So here, what we are doing, we are trying to collect the rain intrusion in the wall of wind under various wind speeds, with and without shutter that you put on the windows. So one of the middle figure shows how much water you collect when you don't put shutters on the window. And the right-hand figure shows like, if you put the shutter, you have not only you protect your window from debris impact, but you can reduce your water intrusion by almost like 80%. So again, these are some of the findings from full scale that we can do. We also do a tremendous advancement of science. For example, with small scale models, I think we do not capture the peak pressures in the wind tunnel. So on the right-hand side, it's a photo of the Texas Tech building where you see conical vortices visualized by smoke that are happening from cornering winds. When you try to simulate that at a very small scale, which is the red on the right-hand side top, the red figure on the turntable, that's like a matchbox. The results you get are not very good. For example, you can see that on the right bottom plot, the pink dots are the one that are the pressures coming from the full-scale data, but the blue lines are the ones that are coming from the wind tunnel, and there is sometimes a difference of 2. And this happens because of the scaling errors when you go much small scale. So we came up with a method where we can test a larger scale building at the wall of wind and still get some good results. So it's based on what we call a partial tolerance simulation, and it deals with a lot of statistics. But it can predict pressures that are accurate and very close to the field. For example, in this picture, in the red circle, you can see that the full-scale data and the 1 to 6 model data, which is the green dot, are very close, as opposed to the 1 to 100 data, which are like far from apart. So the pressure coefficients of minus 18 you can get at full scale and using a 1-to-6 model. You cannot get that with smaller scale. And this partial turbulence simulation method went into the AC 4912, which is the wind tunnel testing for buildings and other structures. So they have a provision there that calls out for such kind of simulation for large scale testing. Once we have these kind of test methods available, you can do a lot of things. For example, this is an example of roof pavers that you're doing on the roof. These are actual concrete pavers. And you can appreciate that there is gap between the pavers, and also there's a gap underneath the pavers. So the gap between the pavers on the right picture is called G, and the gap with the roof surface is H. So the ratio of G by H determines how the pressures are equalized between the upper surface and the lower surface, and how the vortices behave. So we plotted various pressure diagrams using the entire PV roof, using the entire paver roof. And we made recommendations of how, as you increase the G by H ratio, actually what happens is you have less of net wind uplift on these pavers. That means your failure wind speed is higher. So we put these recommendations again in AC 722 and ANSI SPRI RP4, which has guidelines for pavers. So this is how large-scale testing at our facility can again influence like building codes and design guidelines. Similar things can be done with any kind of roofing elements. For example, shingles. Here you can see as the wind is coming from the 45-degree corner, the shingles are billowing up. This is not captured in regular testing in smaller facilities because it's only tested for head-on directions, wind coming perpendicular, not at a corner. But we can see that from these kind of tests, we can see the failure modes can be very different. So we understand about the failure mechanisms when we look at these kind of testing. Again, this is an advantage of the wall of wind. Recently, we have included PIV measurements. So you can see like this is a shake the box where you can see seed the flow field with particles, helium bubbles, and you can see how the vortices are developing. And what we are trying to capture is again, on the left-hand side picture, the smoke shows how the conical vortices form on a roof. But with the smoke, you don't have much flow characterizations, but you can have a lot better flow characterization with the actual velocity field on a spatiotemporal scale using the PIV. So any of you have requirements of understanding fluid structure interaction and fundamental fluid mechanics can come to our facility and use PIV. We do a lot of mitigation. So here is an example of mitigation. So again, you can see conical vortices on the left-hand side picture, which has a lot of gravel scouring on the roof. But we added wind turbines on the edge of the roof, which is a right video. And you can see that those vortices are broken down and there is no scouring. Actually, what is happening, these wind turbines are taking the energy from the wind, breaking down the vortices and reducing the wind load by as much as 60%. At the same time, it's producing wind energy that the building can use during power outages that we have seen in hurricane. We have seen in Hurricane Wilma and even Hurricane Irma. So if we can produce power from these things, we can power a house during these power outages. The right-hand side graph shows how the wind pressures were reduced. So the baseline case is the blue, and then you can see all the other cases like the red dotted are like significantly lower wind pressures on the roof. So this is a multi-faceted device that can reduce the wind load at the same time can produce wind energy. We can do a lot of testing on also other renewable energy systems like PV panels. You can see here we are capturing vibrations of some of the PV panels at full scale. And we are coming up with various wind loads that are related to vibrations of PV panels, which are not really accounted for many PV structures on the roof. And even the current elevated PV structure, like you see on the carport or on the roof of a building, you have an elevated structure with PV. We don't know the dynamic loads of those. So wall of wind can do that. These are some of the plots from those testing that we get from the PV panels. Again, you see like some of these green dots are over what is in the building code. So again, we can see how much underestimation is there in the current codes, and we can inform those code provisions. For infrastructure, we have done aeroelastic testing on multi-span transmission line systems. Here you can see transmission towers and cables, or what we call conductors between the transmission towers. They are dynamically simulated in the wind tunnel. From here, we learn about gust factors that are used to design these towers and cables. And one of the things that you can see, like from the right-hand side picture, the conductor gust factor is about 0.7, but some of the things that we have measured, all the other lines, the green line, are significantly higher. So we are again going to the AC 74, which has provisions for gust effect factor for these kind of designs of multi-span transmission lines, and we are kind of informing them using this advanced knowledge. Same thing goes for bridges. On the left-hand side picture, what you see is vortex shedding. So you can see the bridge going up and down the section model. That's under vortex-induced vibrations without any mitigation. Okay. And sorry, on the right picture, we modeled similar bridge, but at much larger scale. This is my former PhD student, and we came up with diverging vortex generators at the bottom of these bridges to reduce some of these vortex-induced vibration effects. And again, because we can get higher Reynolds number at these large scale, the effect of these mitigation techniques are much more well quantified at the large scale rather than the smaller scale. This is Jonas, Dr. This is a part of research. So here we are seeing like traffic signals that are getting vibrated in the wind. And there is a critical wind speed at which there's some instability that happens. So as you can see, as we are increasing the wind speed, you have a lot of motion there, right? And then due to fatigue of these connections, they break. So the full scale is a very nice way of capturing these kind of instabilities and redesigning these systems that are not very much possible using scale model results. When we do all this testing, we try to involve students, both graduate students, undergrad students, even high school students. They come here and do competitions to learn about hurricane mitigation. And we involve teachers. So on the left-hand side pictures, these are our RU students that come from other universities and work during the summer at the Wall of Wind and learn about wind mitigation. On the right-hand picture, it's basically teachers from those high schools. They come and do a short teacher training course in the summer. You can see they're building wind tunnels. The white is the structure is a wind tunnel that they produced, and they can take it to their schools and teach their students, basically to get them interested in STEM education. So where are we going next? Right now, what we can do, we can simulate some of the high winds in facilities like Wall of Wind. At the University of Miami, you can do at some scale models, wind and water. But there is a lack of full-scale testing facility that can do wind and water both. So we got a project about 13 million for the design, which we are calling the National Full-Scale Testing Infrastructure for Community Hardening in extreme wind, surge, and wave events, and we call it the NISH. So with the climate change, as we all know, the hazards are kind of intensifying. The exposure is increasing. 40% of the US population are in the coastlines, and they are right in the threat from these natural hazards. On the graph on the right hand side, you can see like how the losses per year, cost per year is escalating. Right now, the average is about 80 billion from windstorms that we have lost every year. So there is a clear benefit that if we can do a proactive adaptation, then we can kind of combat against this climate change, climate change impacts. And we know that every dollar invested, in the front end can save like $5 in future losses. So that's the motivation. What is lacking? There's no facility right now that can do at large and full scale the things that you see in this picture, right? So coastal resilience is again a key research question here, how to increase coastal resilience. So the current facility gaps is because of the scale model testing. We cannot go with the similarity requirements that we want to. For example, Reynolds number, Proust number, Weber's numbers is difficult to simulate all of them the way that we want using smaller scale models. Also, when we test scale models, we cannot do destructive testing. We cannot say, okay, under a particular intensity of wind and storm surge, this is how a coastal elevated house will be impacted. Okay. So we want to simulate these high intensity hazards that are anticipated under a changing climate. And we are going to design this facility with the wind speed of about 200 miles per hour and with wave heights that are as high as 16 feet. So the goal is to again have a full-scale facility that will become a national and even a global research infrastructure that can integrate the effect of the notion of convergence. So we are trying to converge their disciplines together. For example, wind engineering with coastal engineering. We are trying to do a methodological convergence. That means we are bringing physical testing, computational simulations, and field data all working together. And institutional convergence in terms of working with various different universities and industry and agencies and stakeholders so that everyone is in the design process and have their input in this design. We did a lot of landscape studies of what exists around the world. So, not only the US, but around the world, what kind of wind and wave facilities exist and what are their scales, what are their capabilities, what are their limitations. Based on that, we selected four facilities in which we are doing testing right now to inform the niche design. One of the facilities is your sustained facility at and on there, we are performing experiments. This one, where we are looking at air-sea interaction, we are looking at the effect of sea spray on structures and various other different things that are informing the niche design. So once the design, what are the research objectives that we want to be answered, basically, right? That's an important thing for us to understand. So as you can see, the first objective is community hazard modeling under combined actions of wind and water. So there are key research questions, right? For example, what are the combined and individual impacts, including the uncertainties of wind, surge, waves, sea spray, and flooding on coastal structures? How much damage to a coastal structure is due to wind or water? Because there is always a debate especially from the insurance companies, is the damage from wind or water? So I think we can answer these questions when the niche is going to be built. What is the effect of aging infrastructure systems and how these things are impacted as they age under different multi-hazard impact? How can you come up with new strategies to increase their resilience? How can we promote public safety and community functionality? Like what methods can we have for saving lives and minimizing the impacts? For example, losing of power, losing of water, or losing of essential elements or the functionality of building following an hazard event. How to promote recovery, right? Also, how to enhance computational modeling of multi-phase fluid structure interactions. So now you have wind and wave and the interface at various scales. So how can you improve computational models? Then how can you kind of couple all this information with regional scales? Because things don't happen at a building scale. You have to model the entire community. So how can we get results from an individual building in the lab and then model what is going to happen to the entire community with similar buildings, and how this is going to inform decisions so that the stakeholders or the emergency managers or the building code can make decisions for residents. The second project objective is closer to what is being done in the is coastal processes modeling. How can we adapt to flood hazards from hurricanes or from other things? Promoting nature-based solutions like live mangroves, dune vegetation, salt marshes, coral reefs, looking at very unique solutions like the sea hives by Dr. Landorf. How can we test these kind of things at very high scales and with interacting hazards? How can we validate engineered systems like gray solutions, seawalls, levees, flood protection systems at large or full scales to protect against natural and built environments? What is the effect of these kind of processes on sediment transport and erosion and morphological changes? So what is the impact of joint wind surge wave actions on sediment transport, erosion, nearshore and onshore morphologies or morphodynamics, geomechanics? What could be a solutions to ensure stability of the coastal structure and foundations, because they are impacted by groundwater processes, morphodynamics, and sediment transport. How to build foundations better? What are the research that is needed for coastal ecology and oceanography? Again, something that is related to the facility. How can we study more tides, turbulence, upwelling, stratification, and transport, and all these dynamic processes which are very important from a point of fundamental knowledge. And the last research objective is, okay, we are doing everything for today. How are we going to prepare for tomorrow? Adaptation for a changing climate, and how are we going to promote sustainability? So the first thing is modeling evolving hazards. I already told you, under these hazards, climate change, we are getting stronger hurricanes, wetter hurricanes, slower hurricanes, bigger hurricanes. So how can we simulate the intensity or even the joint probabilities of these intensifying hazards that are coming off because of sea level rise, extreme rainfall, extensive flooding, and things that are beyond new normal? How do we study impacts of those intensified hazards on our ecosystems and built environment and natural systems and critical infrastructure? What would be the disruptions under these future states of the world? How do we promote climate adaptation, right? We want to produce virtual reality in the facility where people can come, stakeholders, and they experience the effects of the climate futures. And based on that, they can come up with climate adaptation policies. I think experiential decision making is a very important point, as has been studied by social scientists. Like, when you experience something firsthand, there is a high possibility that you're going to kind of move and do some adaptation to that. So we want immersive experimentation in the facility where emergency managers, stakeholders can come and learn. What would be the cost-effective retrofit strategies to avoid threats of future climate-driven hazards, right? And also, how do we fight with the non-relevant energy issues and looking at more advancing the renewable energy, harnessing more clean energy from wind, waves, and solar? One of the things that we plan to do is have a huge deep pit in our facility where you can test offshore wind turbines, because they need a much deeper test section. So we want to do that to ensure that we can do research in offshore wind energy. And also we can work with resilient, carbon neutral, net zero embodied energy, new materials, new structural systems that can combat with this climate change and reduce the CO2 in the atmosphere. So this is a picture, very preliminary diagram of how the new facility is going to look like. The flume is here, as I'm showing, is a 500-meter or more long flume. And then inside this building, you're going to have the wind simulation, and you're going to have the wind generation. The wind and water is going to come and hit this structure in the turntable, it looked very small here, but that's a two-story building that we are planning to test at full scale. So we are looking at like almost a 200 miles per hour with a wind test section of 60 feet by 40 feet, probably 20 fans, a water channel that will be maybe 30 feet deep and 500-meter long, with a maximum wave height of 16 feet, testing a two-story building, other infrastructure. The power will be about 80 megawatt. So it's a huge power, and we'll probably need like millions of gallons of water for the testing. Okay. Um, what is the uniqueness that we are going to have with this facility? We are going to first have full-scale structure testing, large-scale structures at 1 to 10 model. We can test entire communities at a reduced scale and morphological studies. We can do wind only, we can do waves only, or we can do combined wind and wave. So we can simulate various hazard scenarios. And then on the computational side, you can do a digital twin of the facility. You can come up with verification and validation of computational models, verification and validation of structural models, and you can have community test beds that can provide data. Again, it's all in the convergent framework of um, hybrid simulation, observation-informed simulations, and field computational and experiment coming all together. So let's go through an example of a convergence approach, right? So let's say we have field observations of a closed event. You can see a picture of a hurricane-struck community, and we see undesirable performance of that community, and the stakeholder comes and proposes a research. So so we want to formulate a stakeholder-centered research, right? Then we can form a digital twin for how to design the experiments. Okay, so this is a digital twin of the experimental design. Once we have that, it will be very expensive to do everything at the full scale. So we might use facilities like the facility or the Wall of Wind facility or other facilities to test few things at a scaled level to get knowledge, first-hand knowledge of what are the first three options that are the best. Once we have knowledge on that, then we can move to full-scale testing using the niche because it will be expensive and time-consuming. Once we get the full-scale data that we need, we can calibrate our computational models or regional scale models, whatever we are trying to calibrate, and then we can upscale that computational model to model the entire community or to regional-based simulation. And from that, we can understand what are the social and economic impacts of various interventions. And finally, we produce the results to the stakeholder. So, and they can implement expeditiously. And in a future hurricane scenario, we can have better results or better resilience of the community. So this is an example of how we can promote convergence research using various tools. The broader impact, this aligns with the NSF's big ideas because the big ideas is convergence research, one, and the other one is mid-scale infrastructure, MSRI, which are the big telescope ships and other kind of things that you see, which are huge investment of NSF. So we are aligned with that. We will definitely maintain an US competitive advantage if we build this in the US over other countries. And we can inform them even for their resilience, their community resilience. We will protect lives and enhance the quality of life. We'll strengthen the national security and economy. And then there will be research translations for practitioners and policymakers, new products, new patents, new provisions. And finally, integrated workforce development. So just imagine right now, a lot of people at the students at the Wall of Wind, they know a lot about wind. A lot of students in the sustained facility know a lot about waves, but now we will have engineers and other scientists that will have knowledge of this entire convergence of wind, water, computational, experimental, field data, stakeholders, and all of that. So it will be a new workforce development for our future. We have a wonderful team, as you can see from this picture, diversely located all over the US and with expertise. and their hard work and dedication of the faculty, of postdocs, of grad students, and all the staff supporting are highly appreciated. And at the end, I'd like to acknowledge NSF for their continued support for this research. So with that, I think I'd kind of, end my presentation. Again, thank you again for listening in, and I'll be happy to kind of to answer any questions.